Hi, it's Dr. Harris with part two of our work in chapter four in Math 111. We're looking at examples of random variables. In the previous section, we talked about binomial random variables. In this section, in this slideshow, we're going to be talking about normal random variables. So we need to do a little bit of an introduction of different types of random variables, and then we'll focus on what we mean by a normal random variable. So uh, I didn't mention this prior, but random variables can be either discrete or continuous. These are terms that I think I mentioned back in chapter one. Discrete variables count something, continuous variables measure something, and that's the same is going to be true for discrete random variables and continuous random variables. So a discrete random variable is a numerical outcome of an experiment in which we're counting something. A continuous random variable is going to be a numerical outcome of a situation where we're measuring something. And so uh, the binomial case, we were counting the number of successes. And so a binomial random variable is an example of a discrete random variable. In this section, we're going to be talking about a specific type of continuous random variable, the normal random variable. But before we get into what normal random variables are, let's just think about a couple of examples where we might think about these situations where we have continuous random variables. We can measure the amount of sugar in a randomly chosen orange. We can measure the height of a randomly selected college student. Or we could look at the measurement of a grade of a randomly selected statistics student. Notice that in the third case, the range is not all possible numbers, but from 0 to 100. Heights aren't infinitely large. There's an upper limit, but we don't know going ahead in exactly what that upper limit is going to be. It's somewhere probably around 7 feet tall. So uh, these are situations where we're measuring something. And so the particular case that we want to be looking at in this section are symmetric unimodal bell-shaped curves. And many such curves, not all, but many such curves have what's called a normal distribution. And so we'll talk about what conditions a normal random variable satisfy momentarily, but we want to be having this sort of picture in our head in this section. We're talking about bell-shaped curves, symmetric, single peak. Uh, it's not the only such type of distribution we're going to be talking about in this course, but it's the one we're dealing with right now. So if we've got a bell-shaped normal curve, the distribution is going to follow what we call the 68-95 rule. So if we were able to identify what the mean and standard deviation were for this distribution, we would know that 68%, again, that's close to two-thirds, it's a little bit more than two-thirds, but about 68% of all values of a normal random variable are going to be within one standard deviation of the mean. About 95%, 19 out of 20, are going to be within two standard deviations of the mean. And almost all, about 997 out of every 1,000 observations, will be within three standard deviations of the mean. So observations that are more than two standard deviations away, we'll comment on this more in a few slides, are going to be considered unusual because they would occur 5% of the time or less. So here is a more specific example of some bell-shaped curves, and that's heights of students. This goes to the UC Davis data set, and here are a pair of density plots where we've separated out by gender. We saw how to do this sort of thing back at the end of chapter 2. And so we're doing a density plot of the variable height. Height is capitalized for the UC Davis 1 data set, and we're separating out by sex. That's also capitalized. And we've given it a title, and the layout equals C1, 2 tells our studio that we want these density plots stacked on top of one another. And what we see is that in both cases, they're pretty close to bell-shaped and symmetric. And so we're going to take these distributions to be approximately or close enough to normal in shape. If we apply favestats, so we want to remember how we did that, we took the numerical variable and broke it down by the categorical variable. And so we get the 5-number summary and the mean and standard deviation for both the female heights and the male heights here. And so what we see is that the mean for the women is about 65.5 inches with a standard deviation of about 2.5 inches. And the men's heights are about 69.6 inches with a standard deviation, again, of about 3.5 inches. So the men's mean is higher, but the men's heights are also a little bit more spread out. And we saw that here. It looks like there's a little bit wider distribution than it is for the females' heights. The female heights are a little more tightly bunched than the male heights are. So we're going to use these numbers in the next couple of slides to talk about applying the 68-95 rule to the women's heights. And then you'll get a chance to work on the men's heights yourself. So female heights have a bell-shaped distribution, mean 64.5, standard deviation 2.5. We're going to round to 1 decimal place here. If we assume that these heights are representative, then we've got an approximately normal distribution for female heights. They satisfy the 68-95 rule. So I'm going to subtract 1 standard deviation from 64.5 to get 62. And I'm going to add 1 standard deviation, 2.5, to 64.5 to get 67. And so we would say that about 68% of all females at this college, this university, have heights between 62 and 67 inches. The other 2 statements deal with adding or subtracting 2 standard deviations, or adding and subtracting 3 standard deviations. So if I want to find out what the 95% part is, I'm going to take 2 standard deviations. 2 times 2.5 is 5. So I'll subtract 5 from 64.5, and I'll add 5 to 64.5, and I'll see that about 95% of all females at this university should have heights between 59.5 and 69.5 inches. And then we do the analogous thing for 99.7. We subtract 3 times 2.5, that's 7.5. So we take 7.5 away, we get 57, sorry, that should be 57 there. So it's 57, and if we add 7.5, we get 72. So sorry for the typo, but 99.7% of the heights should be between 57 and 72 inches. I'm going to ask you to make analogous statements about the males. So you can go back into the output of favstats, identify the mean and standard deviation, round to 1 decimal place, and then apply adding and subtracting 1, 2, and 3 standard deviations away from the mean to get the ranges over which 68, 95, and 99.7% of observations would land between. And we'll go over this in class. So I've been using that word normal. And so if we've got a bell-shaped distribution, many bell-shaped distributions, not all, but they're going to be called normal distributions. And so this is what sort of an idealized normal distribution centered at 0 with standard deviation 1 would look like. Almost all of the area would be between -3 and 3, 99.7% of the area. About 95% of the area should be between -2 and 2. So here, what we're doing is, in situations like this, where we've got these density plots, we're associating the percentage of observations that live on a range with the area underneath the curve over that range. So if I'm going from -2 to +2, what I'm saying is that I should expect about almost exactly 95% of the area underneath this curve should be over the interval from -2 to 2. About 68% should be over the interval from -1 to 1. So we're going to use the Greek letter lowercase mu to stand for the mean or expected value of a normal random variable. And we're going to use the Greek letter lowercase sigma to stand for the standard deviation. So the mean in a binomial situation was n times p. The standard deviation was the square root of n times p times 1 minus p. Here we're not going to have formulas for what the mean and standard deviation are, but we're going to be able we're going to be told what those numbers are, generally speaking. And the mean will be called mu, the standard deviation will be called sigma. We'll be seeing these symbols a lot later on in the course. And so the 68-95 rule is going to apply to a normal random variable. Okay, so let's before we go do some other things, let's introduce a tool that will help us understand whether we have an unusually high or unusually low value, and that's the z-score of an observation from a normally distributed random variable. So if I've got an observation from a normal distribution where I know the mean and the standard deviation, I can calculate what's called its z-score by taking that observation, subtracting the mean from it, and dividing by the size of the standard deviation. And what this does is, doing that subtraction tells me how far above or below my observation is from the mean. And dividing by the size of the standard deviation actually tells me how many standard deviations I am above or below. So again, the sentence right here is a good one. A z-score tells you how many standard deviations above or below the mean the given observation is. And we know by the 95 rule that 95% of all observations land would be within 2 standard deviations of the mean. Another way to say that is that 95% of all observations are going to have a z-score between -2 and 2. So only 5% of observations will have a z-score that's either bigger than 2 or less than -2. So we're going to think about those observations as unusually large if the z-score is bigger than 2, or unusually small if the z-score is less than -2. Let's look at an example that we're going to pay a lot of attention to through much of the rest of the slideshow. Suppose that the mean number of hours on social media each week for college students is 20, and the standard deviation is 4. You can decide whether or not that's reasonable for you, but we're going to roll with it in this slideshow. Suppose you've got a student who spends 30 hours on social media each week. What's the z-score of that student? Well, we take the observed value, 30, we subtract the mean, 20, from it, we divide by the standard deviation, 4. So the subtraction comes first. 30 minus 20 is 10. 10 divided by 4 is 2.5. So the number of hours this student is on social media every week is 2.5 standard deviations above the mean. Since it's bigger than 2, since the z-score is bigger than 2, that's an unusually high value. I'd like you to practice with 2 other students, one of whom spends 16 hours each week on social media, and the other one who spends 7 hours each week on social media. And so compute the z-score in each of these cases and answer the question, is this or is this not an unusual value? And we'll talk about this in class. So we can just state the 6895 rule in another way. If you've got a random variable that's normal or approximately normal, then the probability that the random variable's value is going to fall within 1 standard deviation is about 0.68. And so the way we say this in terms of probability is the probability that x is between mu minus sigma. So mu minus sigma would be the number that's 1 standard deviation below the mean, and mu plus sigma would be a number that's 1 standard deviation above the mean, is about 0.68. And then these other 2 statements have to do with the 95 and 99.7 parts of this rule. If I subtract 2 standard deviations, that's the number that's 2 standard deviations below the mean. If I add 2 standard deviations, that's the number that's 2 standard deviations above. So the probability that x is between mu minus 2 sigma and mu plus 2 sigma is about 0.95. And there's the analogous statement for 3 standard deviations down here. So just a quick example, going back to our social media situation. If mu is 20 and sigma is 4, we want to fill in the blanks here. What are the numbers that should go in these 2 slots so that the probability that x is between those 2 numbers is about 0.95. Well, if sigma is 4, we know that we want to be within 2 standard deviations of the mean. We'll be within 2 standard deviations of the mean 95% of the time. So we want to calculate the numbers that are 2 standard deviations below and 2 standard deviations above the mean. If the standard deviation is 4, 2 standard deviations is 8. So I'll subtract 8 from 20 to get 12, and I'll add 8 to 20 to get 28. And so the probability that x is between 12 and 28 would be 0.95. So just a couple more things before we stop the slideshow, break it off into 2 parts. The RStudio command that we're going to use to find probabilities for normal distributions is pnormgc. not everything, not all the numbers fall nicely being 1, 2, or 3 standard deviations away. We have plenty of other numbers that we can work with. So suppose we want to know what's the probability that a student spends more than 18 and a half standard deviations or 18 and a half hours on social media each week. The command we're going to use is pnormgc, and it's going to be set up a little bit like pnormgc was. We're going to put a number in here or a range. We'll define a region. We will want to specify what the mean and standard deviation are. We use mean for the mean and SD for the standard deviation, and then graph equals true will put a graph for us. So let's put this into our studio. And we get something that looks similar to what we did with pnormgc, but it's a little different. It's smoother. We have a normal shaped curve here, but we do get a probabilistic answer out as well. And so the probability that our number of hours spent each week on social media is bigger than 18 and a half is about 65%. So again, let's go back and look at this. We give a range, we specify a mean and standard deviation, we give a region, and we tell graph equals true. And the region that we get is going to be determined by the inequality that we have. If I had less than instead of greater than, I would put 15 in here and I would change the region to below. So I'm not going to go into RStudio to show you, but the output would be this. So the probability that x is less than 15 is about 10.5%. We can do between probabilities as well, as we did with pnormgc. If we wanted to know what the probability that the number of hours is between 15 and 22, we would put C 15, 22 here and change our region to between. Mean and standard deviation stay the same. We still get a graph. And so here is our shaded region. Again, it's between 15 and 22, and we get about 58.5% probability. But we can also do an outside probability, and this is going to be something that we're going to see a fair amount of in future chapters. So suppose we want to know what the probability that we spent fewer than 17 or more than 27 hours on social media each week. Then we would give these two numbers, C, 17, 27, but by changing the region to outside rather than between, we're going to get the two regions that are on the ends, the two tails in our distribution. And so here's the region below 17, here's the region above 27. And so they're both shaded in. The combined area is about 26 2/3. So it's about a 0.267, about 26, 27% chance of this happening. So we got four options here: above, below, between, and outside. One more note before we stop this slideshow, and we'll move on to we have a little bit more to say in part 2. You may have noticed that all the examples that I gave you so far had less than or greater than in them, and not greater than, equal to, less than, or equal to. And the reason for that is that while it makes a difference in the binomial case, in any discrete random variable case, it doesn't make a difference whether we talk about less than or equal to, or greater than or greater than equal to in the continuous case. And I want to argue that the probability that in the continuous case that x takes on any one specific value, is actually equal to 0. So let's take a look at this. Suppose I wanted to know what's the probability that a student spends exactly 23 hours on social media each week. We're not talking about rounding here. We're talking about just exactly 23 hours. And so I would do C 23, 23. I started 23, I'd ended 23. My region is between. So I'm going to treat equal as less than or equal to 23 and greater than or equal to 23. Mean and standard deviation aren't changed. Graph is still true. And what I get from a graphical standpoint is I just get a vertical line segment here. And we know that there's no area. The segment has no area. And so we would expect the answer to be 0. So the bottom line is it doesn't matter whether we have a greater than or a greater than or equal to. It doesn't matter whether we have a less than or a less than or equal to. Those probabilities are going to be the same. So it's okay just to use less than or greater than all the time. But But if it says less than or equal to, you can put that in there. It's not going to change the value of the answer. So we've got a little bit more to say about this, but we'll continue that in our next video.